Welcome Gregory Schwartzman, who will be talking about SGD through the lens of Kolmogorov complexity. Yeah, thank you.
For the introduction. So yeah, today I'm going to be talking about connection between SGD and Kolmogorov complexity. I'm not an expert of any of these fields, but hopefully it will go well, okay? So throughout this talk, I'm going to be trying to answer just like one very simple question, and I will give you answers which will be conditioned on some assumptions, but the question is very simple. Does local progress for SGD imply global progress? And specifically what I mean, so SGD, stochastic gradient descent, and it's a very simple algorithm. You have some data, you pick a batch randomly, you have some model, you train that model on the batch using gradient descent, you get a new model, and you repeat, pick a new batch, train the model, and so on. Now consider the following scenario. Imagine that after the gradient descent step, or actually before the gradient descent step, the model that you have gets like 50% accuracy on the batch. Then you do the gradient descent step, and the model gets 100% accuracy on the batch. Okay, so very nice. This is what I would call very good local progress. And now the question is, will we eventually get good accuracy on the entire data set that is global progress? Okay, so can it be that you will just keep getting this local progress and never get to anything good, any good accuracy on the entire data set? Okay, and let me kind of give you an outline of the talk. So the structure of this talk is going to be a little bit strange and non-standard. So usually you would present your results and then kind of go into the details. I'm going to not talk about anything that I do for like half of the talk. I'm just going to be talking about this method, which is called entropy compression. And it's really cool, and you should at least get an intuitive feeling for it. Then I'll be kind of looking at how to apply this to SGD. Okay, so we're going to try to fit SGD into this framework. While doing that, we'll see that we need some assumptions. Okay, then I'll tell you which assumptions I'm actually making in this paper. I'll try to justify them, motivate them. And only in the very end, I will actually state the concrete results and briefly say something about the related work, although this is really not comparable, and in the end, you'll see why. If you have any questions, just stop me, okay, at any time. Okay, so to present entropy compression, I am taking a toy problem, and hopefully this will give you like the main idea of this tool. So I have on the left a grid of light bulbs. Every light can be either on or off. On the right, I have a piano, and when you press the piano, it switches, every key will switch some of the light bulbs on, and some of the light bulbs will go off. And to be more specific, every key controls at most one light bulb per line. So this red paw mark, by the way, means that the key is pressed. The key can be either pressed or unpressed. When you press a key on one line, at most one light bulb will go on or off. Every light bulb corresponds to a single key, so you can't have two keys controlling the same light bulb. And the last assumption is going to be a very vague one, that no key affects too many lines. Okay, you'll see in the end why I'm making this assumption, and I'm not telling you exactly like how much is too many, but hopefully this won't be an issue. What is the goal of this problem? Well, a line is good if at least one light bulb is on. Otherwise, we say it is bad. The goal is to press the keys on the piano in such a way that eventually all of the light bulbs, all of the lines are good, okay? And the question is, how do you solve this? Like, what's an algorithm for this? So before I get to an algorithm, any questions about this problem? Okay, I should just say this toy example is actually what I will show you now is the Moser-Tardosh algorithm for a constructive version of the Lovash local lemma. The light bulbs is like a KCNF. The piano is like assignments to variables, but it doesn't matter. You don't need to know all of that. But if you're familiar with that, then this is what you're saying. Algorithm. I have a video. Okay, so you take your favorite pet and you let it smash the piano around. Okay, and eventually it solves it. Okay, and the surprising part here is that it will solve it quite quickly. Like it's not exponential time. It will be very, very fast. Okay, so let me try to be more specific. Let me try to kind of define this in a better way than a cat and a piano. First, I'm taking the light bulbs on the left and I'm giving them unique IDs. Now I'm defining this procedure called fix. Okay, the idea is that fix gets an ID of some line and it tries, okay, it will eventually fix the line. In a sense, at least one light bulb will be on when this thing returns. Okay, and furthermore, it won't mess up any other lines. So what does it do concretely? So just to remind you, so let's say we have 5 light bulbs per line. We say that for one light bulb, there is one key controlling it. So there are pink keys outlined on the keyboard. For each key, we flip a coin and we set it either pressed or unpressed according to the value of the coin. This, of course, changes the situation of the light bulbs. Okay, so it might be that now the line we're trying to fix is good, but maybe we broke something else. Maybe we didn't manage to fix it. It's kind of random. It's not an issue. What we do is we're going to recurse now. Okay, so these lines in turquoise are lines such that the pink keys on the keyboard affect them. When you press one of the pink keys, one of the lines will change. The lines not in turquoise, let's say line number 3, is just lines not affected by these keys. Okay, so roughly speaking, when you make this random assignment, there's no way you're gonna do anything to line 3. Okay. Okay, so we're gonna call this procedure recursively on all of these lines. You might also call it on the line you're currently trying to fix. It's not an issue. And we will just do that. Like this is an unbounded recursion. We'll just do that until it returns. Okay. So now let's say we recurse, and now we try to fix line number 2, and so on. So this is a very, very silly procedure, but at least correctness is guaranteed. Okay. So when this thing returns, you are sure that like what you were trying to set up, what you were trying to fix in the beginning is good, and everything that is intersecting with it, like the keys that affect it, that's also good. So you didn't mess anything up. Okay, so the correctness should be direct here. What you should be suspicious is, okay, this thing should never stop ever. Now using this auxiliary function, we can easily solve the problem. Like easily, like correctness-wise. So we start with some random assignment. We press the keys, and then we call this fix procedure for every line which is bad, that is no light bulb is on. So again, correctness should be clear here. What should be surprising is that this terminates in polynomial time. Okay, so I think either linear or quadratic in the number of light bulbs or something like that. Okay, so like very, very fast for an algorithm which is this silly. And what I'm going to show you is more of an intuition of why this terminates. And I need to introduce Kolmogorov complexity and so on. But before doing that, are there any questions just about the algorithm? Just like, do you understand the mechanics of what's going on?
I mean, why wouldn't it just terminate in, I mean, number of keys on the keyboard? I mean, isn't it like simply a linear system at the moment?
But you're doing like random assignments, right? You just keep putting random key presses. So why would it even? Like,
why am I not just trying every key and then I'm done?
why are you not, because the key, it can turn off some of the light bulbs. Like there might be
turn off.
Yeah,
still,
yeah, maybe
okay.
I wasn't clear about that.
I thought it can only turn on, but okay, yeah.
Okay, is that okay now?
I mean, sort of, yeah.
Okay, for now.
Okay.
Any more questions about this? Okay, then I will introduce Kolmogorov complexity, and we'll go on from there. Okay, Kolmogorov complexity, maybe you're familiar with this. The Kolmogorov complexity of a string X is just the shortest Turing machine which outputs X. We denote this by K of X. Know that this definition is a little bit vague, like what encoding of Turing machine, how many tapes. It doesn't matter. It really doesn't matter. What we are using, the property that is very important for this talk, is that if you take X to be a random binary string of length n, then with high probability, its Kolmogorov complexity is about n. Like it can be smaller by like a logarithmic factor. And this should be, again, very intuitive. If I give you a random string and I tell you, please write a program that outputs this string, like the best thing you can hope for is like print string, and that's how your program will look like. Another thing I need to introduce, again, I won't be using this for too much, just maybe a little bit notation, is a conditional Kolmogorov complexity. So this is the size of the smallest Turing machine which outputs X given Y, and Y doesn't count towards the size of the Turing machine, okay? So for example, the conditional Kolmogorov complexity of X on itself is just a constant, okay? Okay, now how do we use this to bound an algorithm which has an infinite recursion? Okay, there seems no connection here. So let's just focus on this procedural fix and kind of see what it does. Okay, so we are worried that the depth of the recursion can be very deep. It can call fix and then fix and then fix and then fix. One thing which should note, the more you call this procedure, the more random bits you're generating, okay? And these random bits should not be compressible algorithmically, okay? And this is an important point. What I will try to show you, again, very, very hand-wavy proof, is that starting from the last call to this procedure fix, I can get starting from the last call, plus some hints, I can go back in the recursion tree. I can like reconstruct the state of the system back to the start when you first call this procedure. Okay, this means I can reconstruct the random bits, and we will see that this will lead to a contradiction. Okay, so it will lead to a contradiction because on the left, okay, to reconstruct all of these random bits, I have the state of the system in the end. Let's say state of the system is like the state of the piano after we called this procedure for a bunch of times, plus some hints that will allow me to reconstruct the recursion tree. And the hints will be such that this will be smaller when counting bits, for example, than all of the bits on the right. And let me be a little bit more specific. So this is just an outline of what I want to do. And let me kind of try to convince you why you can even do something like that. Okay, so let's look at a specific call. So just to remind you, what does fix do? It takes some configuration of the system. So this piano on the red, it flips some random bits, it presses some keys, and then you get this piano on the right, the blue piano. And then we recurse for some different line. Now, just a thing to note, the blue piano, the configuration of keys is the same on the top and the bottom. Note that in the bottom, the pink keys became light blue keys. This is just because these are the keys that affect the light bulbs on that line. Okay, it's not super important, but just to avoid the confusion. So how do I go back? Like, let's say I'm in this fix M and I want to go back to fix 2, like reconstruct the entire state, where the entire state would be, well, knowing this parameter 2, and also the state of the piano and the random beats? Well, I need some hints, okay? Specifically, a very direct hint would just be the ID. Like if you would tell me, okay, listen, before calling fix m, we called fix 2, and this is what led to the state. And then you think that you're basically done, but there is like one tiny point. How do I get from the blue piano back to the red piano? And the important thing to note is that when we called fix 2, all of the lines, all of the lights on line 2 were off, okay? And there is exactly one key configuration that does that, okay? So knowing that we are fixing 2 and knowing the blue piano, we can go back to the red piano. This also gives us the random beats of the system, okay? And okay, so actually before I talk about compressibility, is this clear? Maybe I'm not saying anything smart yet, but just like the whole idea. Like if you give me the ID, I can reconstruct the random beats. Is that part okay? Okay.
Excuse me.
Yes.
I just wonder if we know M at the beginning or not.
You can know M in the beginning. It's not a problem. You can know M and all of this grid on the right and which key affects which light bulb. That's fine. Like all of this knowledge or these bits, I'll say something in the end, but it will be asymptotically smaller compared to the random bits and the hints when we go very deep in the recursion, okay? Because these things don't change. Their size does not depend on the time of the execution or the depth of the recursion. Is that
not important?
Yeah, so is it okay? Okay, so the next thing I want to say is something about compressibility. Okay, so like until now, you should be kind of convinced that I can reverse this process, but I need some extra information, okay? But just I want to remind you that we made some assumption in the beginning, and the assumption is that a key does not affect too many lines, okay? If we wouldn't have made that assumption, then just going from a fix M to fix whatever, you need at least, let's say, log M bits to encode this. But now you can do this much more efficiently, okay? Because keys don't affect too many lines. So if I'm in line M, there's only a small number of lines that can kind of cause the recursion to go there. So I don't need to encode all of the M lines. I need only a subset, okay? So for example, maybe 4 bits are enough to encode these hints. And for every time I go up in the recursion, I manage to recreate five random bits. So basically, what do we have? We have the state of our system in the end. Okay, so we have the final configuration of the piano. We have the light bulbs, and we know how they connect to the piano, which key affects what. And these blue arrows are like the hints we need to reconstruct everything back. So we can reconstruct all of the configurations, and we can reconstruct all of the random bits, okay? So now it's just an exercise of like what is bigger. And recall that the number of bits, that's proportional to the number of iterations or the depth of the recursion. So even if we go to a shallow depth, if we run this procedure only 2 times, we get a few random bits, and that is much smaller than the encoding the piano, the light bulbs. That will be the dominating part. So we don't get any contradiction. However, if we run this for a long time, sufficiently long time, what's going to dominate asymptotically, right? Because the more you run it, encoding the bulbs and the piano, right, just in the final configuration, it still requires the same amount of bits. What's going to dominate is encoding these blue arrows, the hints, and we're saying that these are much smaller than the random bits on the right, okay? So you'll get a contradiction, okay? So this is what basically gives the proof that the depth of the recursion must be bounded, and then you get a nice running time on this thing, although just looking at the algorithm, you would say, why would this ever work? Any questions about this? I know it's a bit hand wavy, but just intuition wise, is this okay? Okay, if this is okay, let's try to see what we can learn from this example. Specifically, like how would you use that to show that your algorithm, your favorite algorithm, terminates? So first, you need a randomized algorithm, of course, but you need that the number of random bits is proportional to the number of iterations. You need that the algorithm is reversible in some sense, that is, you can reconstruct the randomness, and it's fine if you use some hints to do that. But the hints need to be sufficiently small, that is smaller compared to the randomness you're getting. So let's take this and try to apply this to SGD, okay? And specifically, I want to show you that this would imply that local progress would imply global progress for SGD under some assumptions, which I will tell you a bit later. Okay, just to remind you, you already seen this slide, but just what we want to show. We want to show that if you keep getting this local progress on batches, you should also get global progress on the entire data set. So one thing to note after looking at this SGD algorithm is the first line of our entropy compression cookbook is already good. We can put a check mark on it, because the longer you go, the longer you iterate, the more random batches you generate. The more random batches you generate, the more random bits you need. So the random bits is proportional to the number of iterations. So we're off to a good start. So now I'm going to do some kind of definitions, just so we're on the same page of what I'm proving. So I'll have a data set, okay? And the data set has n elements, and every element has a unique ID. It includes some data, so a picture of a cat or a dog, and some label, okay? Cat or dog. We will also have a model, okay? For this talk, a model is just going to be a d-dimensional vector of real numbers, and this just corresponds to a function, right? So imagine this is just the weights of some neural network. Note it's very common for models to be over-parameterized, so d can be much larger than n, okay? Although we don't demand it, okay? But it works either way. And finally, we assume that we have finite representation for real numbers. So we're using floats, okay? We have a loss function, okay? So we define this like for every element, there is a loss function, like squared loss. Every such loss function is differentiable and L smooth. L smooth just means that the gradient is Lipschitz with parameter L. And we also define this notion for sets, okay? So for a subset of X of the data set, I define f of A just to be the average loss over elements in that set. And the goal here is to minimize f of X. X is the entire data set. I should just say that I'm defining these notations, but what you're going to see for the rest of the talk is just like functions of subscript cats, and then input a picture of a neural network. Like I won't be doing any math as things go along. One last thing I need to define is the accuracy of a model. Okay, so for any subset of elements in X, We define the accuracy as just how many elements does the model classify correctly. Well, classify is kind of implied by how you round the loss function. It doesn't really matter the specifics here, okay? But just so we're clear, if I am asking about the accuracy on a set of 4 elements, I can get either 0, 25%, 50%, 75%, or 100%. Okay, great. Okay, just let me describe the SGD algorithm. So this should be the standard vanilla SGD algorithm with like one thing that's different, okay? So we start with an initial model, and that model is randomized. We have epochs, and unlike in real life, I'm not bounding it, okay? So I'm just looping forever, and I have a stopping condition later on. In every epoch, I take the entire data set, I shuffle it, and I divide it into batches, okay? For every batch, okay, this would be an iteration, I do the following. And this is the non-standard part that I use only for analysis. I check if the model that I currently have on hand, okay, at the current iteration, if it's good in the sense that it gets good accuracy on the entire data set. So I'm asking, is the accuracy of the current model on the entire data set greater than some threshold, okay? And then I continue doing a gradient descent step. Okay, so I'm gonna say a few more things, and then I'm gonna talk a little bit about that last point, because I know that people don't like it so much. Okay, the batches will be ordered tuples rather than sets. That's gonna be more convenient for us. This B, the size of the batch, I'm gonna define it later, but it's not too big. It's like about polylogarithmic in the size of the input. This termination threshold, let's assume for now that it's constant, although it doesn't have to be, and the alpha is just the learning rate, okay? So I want to show, using entropy compression, that this algorithm terminates, okay? This algorithm only has one way to terminate, and that is when the condition on the second line from the bottom holds, okay? This implies, okay, that if you run SGD, even without this condition for long enough, you will get the condition to hold in a sense, right? Because they're doing the same thing. So basically, this will showing that this thing terminates will show that eventually you'll get a model that achieves high accuracy on the entire data set. Is this okay? Is this confusing? Okay. So let's start. Let's try to say something about SGD using these.
I'm sorry. Can I ask a quick question before? So could you here check the accuracy on some kind of validation tests to make sure that you're not overfitting? Or
sorry, I can't hear so well.
Is it? Sorry, I have to change this. Can you hear me better?
Like a little bit. Try again now.
Yeah, can you hear me better now?
I think so, yes.
Yeah, I was just wondering, because you're checking the accuracy on your training set here to terminate the algorithm, right?
Yes, I'm checking the accuracy on the training set to terminate the algorithm. I should also
sorry, so I'm not using the validation set.
Yeah, okay, so yeah, I should have said in this, what I'm talking about here, there's only the training set, there is no evaluation set, there is no test set. It's only like, can you even for the training set, can you eventually get like a good accuracy? But you're right, like you could implement this condition in practice, but like by sampling some subset of the entire set and actually do that. Is this what you mean?
Yes, exactly. Thank you.
Okay, thank you. Great. So let me try to say something about SGD and the reversibility. Okay, so what do we have? In the ith step, we take the model, we take a batch, we get a new model. Okay, what I can tell you is that if I have the batch at step I and the model at step I+1, I can reconstruct the model at step I. So I can reverse the gradient descent step if the learning rate is sufficiently small, okay? And this is not, I'm not giving an efficient algorithm here. This thing uses the part that our real numbers have finite representation and L smoothness. Like basically, it's a brute force search to find the one correct model that leads you to this WI+1 using a gradient descent step. Okay, so we do get some reversibility, but it's a silly kind of reversibility because, like, well, this BI, the batch, is like my randomness. So I'm saying, if you give me the randomness, I can go one step back and then maybe I can reconstruct the randomness, but I already have it. So it's a silly thing to say it like that. But it will be useful. It will be useful, I promise you. What we really want to say is that given the model at step I+1 and some hint, which is not too big, I can reconstruct the batch one step before. Okay, using that batch, I can reconstruct the model at that step, okay, and I can repeat this process. So just, okay, so you should be semi-convinced that the algorithm is reversible, and I have an illustration here that will convince you a little bit more of what I want to do, okay? So I want to start, okay, so let's say, how do we reverse like one epoch? I want to start with the data set and the model at the end of the epoch. Now I have a bunch of hints, okay? And I'm going to do the following. I take the model at the end of the epoch and the hint that corresponds to that model. I haven't sent what the hints are yet. Yes, this will come later. Then I will reconstruct the batch, okay? So I reconstructed some randomness. Using that batch and the model, I will reconstruct the model one step before. Then I will take the appropriate hint and reconstruct the batch one step before. And I will continue this until I've reconstructed all of the randomness of the epoch. Okay, so like this is the idea. This is the attack plan. So I'm gonna get on with like proving it, like giving like two examples of why you should believe me it works. But first, there's like two cases. One case is like an easy case, which is not what is in this slide. And then will come the second case, which is more or less what is in this slide. So let's start with the first case. Let's call it the easy case. Okay, so in this case, I will just try to recreate the entire permutation of the data set, not doing it like batch by batch by batch. I'm gonna say that there is a scenario where I can just reconstruct all of the randomness of the epoch, okay, efficiently, okay? So just to be clear, how many bits do I even need to represent such a permutation? Well, this is log n factorial. You apply Stirling's approximation, and you get n log n over e plus some logarithmic factors, okay? So I want to show you that under some assumptions, I can get back this entire thing, all of these random bits. And to encode this, I will need less than this. I will need less than this amount. And this would mean that, okay, we can use entropy compression here, which will imply that we finish, or that this can't happen too much. Okay, so what is the scenario? What is the scenario in case one? In some iteration in the epoch, I get that the accuracy of the model on all of the elements it has seen so far is sufficiently larger than the accuracy on the elements it hasn't seen so far, okay? You can also flip this inequality and it will work just as well. And if this holds, I can compress the entire permutation for the epoch, okay, in an efficient way. Okay, so I will convince you by a toy example. Okay, this is the silliest toy example that you can think of. Imagine there is this miracle scenario where dead in the middle of the epoch, you get that the accuracy on everything you've seen is 1. So the model classifies everything correctly, everything you've seen so far. And all of the data that you haven't seen, it just misclassifies. Okay, so this will be our toy example. And so if we have the data and the model, I can immediately get the elements. Okay, I immediately know which elements are on the first half of the epoch, right? The ones that are classified correctly, and which elements are on the right part of the epoch, elements that are classified incorrectly. So all I need to do is to encode 2 permutations, but shorter, of length n/2. Okay, and as you see, there is a minus n factor here, and this is the amount of bits we save by doing so. So what is our hint? The hint will, of course, be the permutation, but that's not enough. We also need like the model, but not really the model. We need the accuracy function, or specifically the binary function, which tells you for every element if the model classifies it correctly or incorrectly. And this function will need to be kind of a simple function. That is, to encode this function, we don't want its Kolmogorov complexity to be so high. So here I'm going to go on a tangent, okay, about this assumption and why would you assume that and why do I need to assume that? But at least up until now, do you get this example? Is this clear? Is it unclear? Think about it. If you can stop me also like a few slides down the road and tell me like, go back. I'm open to that. Okay, so first assumption that I need. Models compute simple functions. Specifically, the Kolmogorov complexity of the function computed by the model is smaller than n times something, some constant for the sake of this discussion. And you see this and you should immediately like be super suspicious. You should be like, what? You said that the initial model is random. Doesn't this immediately mean that if the model is over-parameterized, you get that the Kolmogorov complexity is much bigger than n, and then this entire assumption makes 0 sense? And no, it's actually not the case. The model has high Kolmogorov complexity. It's a very long string of zeros and ones, much longer than n. But the function, like the accuracy function implied by the model, can still have like very small Kolmogorov complexity. Okay, and the best analogy here is imagine a very complex polynomial over a field that always evaluates to 0. If you want to give me the polynomial, you might need a lot of bits, but just the function created by the polynomial, super easy. Okay, this might still not get you convinced. Okay, so it's not, it's not impossible. Why would it even be reasonable? It's surprising there is like a line of research that people are looking into. Like people are looking like what is the Kolmogorov complexity of things when you initialize them at random. And surprisingly, there is some work that shows that randomly initialized models are biased towards simple functions. That is, you are more likely to get a simple function than a complex function. So the literature that I found was mostly like for very, very simple models when you want to like formally prove something. They also have some kind of experiments that show that the function learned by the network is also simple according to some measure. It is something, again, measuring Kolmogorov complexity is impossible, but they had some proxy measure for that. So like from the research that I could find, it suggests that this might be a pretty reasonable assumption. But you need to decide for yourself if you accept this or not, okay? Okay, let's continue. Any questions until here before I continue to the second case of this paper?
I mean, about the sensibility of this assumption, I mean, it would have to have small Kolmogorov complexity, but it would also have to be kind of distinguishing the different permutations, right? It should have a smaller accuracy on exactly one of them. Can these two even go together? These two assumptions.
Should be distinguishing different permutations.
Yeah, you assumed that on one of the, not permutations, different batches. On one of the batches, the accuracy is significantly better than on the others.
Yes.
So that's an assumption on the function. And so the question is, if this is not like somehow in conflict with the low complexity assumption already.
But the permutation is already fixed. But I kind of see what you're saying. Do you have an intuition why it wouldn't hold?
No. Okay.
But I get it. Like I get this assumption, like why people don't like it. Okay, let's get back to this at the end of the talk. But like very good point. Okay, second case. So let's assume that the first case doesn't hold. So throughout the iterations, we never get this kind of huge discrepancy. Okay, that is the accuracy on let's say what we've seen so far and what we haven't seen is not off by too much. And you can show that these two things. This also implies that these accuracies are not too far off than the accuracy on the entire data set. Okay. Okay, so let's try to encode batches, and let's start with how would we encode batches naively. Okay, so to encode a batch, okay, you just need to pick the B elements, and then you need to order the batch. So this is the expression that you get. Now, recall how we reconstruct the batches. Okay, I told you that we're going to reconstruct them from the end of the epoch to the beginning of the epoch. And once you've reconstructed some batches, it's easier to reconstruct the next batch. Okay, that is, you know that some elements kind of cannot be in that batch. Okay, so the space becomes smaller and smaller and smaller. Still, this is still kind of, you know, the trivial way to do it. I'm not doing anything smart, right? To do something smart, I have to somehow use the model, right? I have to say, well, but you know, with the model, I can even get that space of possibilities. I can get it even smaller. And here you need some assumptions on the model, right? If I don't make any assumptions, you know, there's no way to get out of it. So let's make some assumptions, okay? And this assumption is the local progress assumption. And basically, this is just a formalization of what I showed you before on in the picture. And basically, I'm looking at the average of improvements over the epoch. And I want to say that this is greater than some threshold. So for example, first I got it from 50% to 60%. And then I got it from 40% to 50%. Then I got it from 50% and went down to 45%. You take all of these differences, the plus 10%, minus 5%, you average them out. And if over the epoch, on average, this is greater than some threshold, we say we have local progress. Okay, so again, I will try to one thing. So you see there is this progress parameter beta, and it's not one parameter, it's parameterized by epsilon. Like for now, don't worry about it. Assume it's a constant, small constant. So I will convince you, I'll try to convince you again with a toy example, but believe me, it works beyond the toy examples that I'm showing you. Okay, so imagine the following scenario. You get 80% accuracy on the batch before the gradient descent step, and then after you get to 100% accuracy. Amazing. You have this miracle happening over and over and over again. And to finish, you want 90% accuracy on the entire data set. So will this terminate? Will this not terminate? So let's look proof by picture. How can I show that? Well, I will show you that having this assumption on the model will allow me to reduce the number of potential elements from which the batch can be recreated. And this should kind of convince you that, oh, okay, so we can compress it more efficiently. Okay, so what do we note? So note that this is not case one. So the accuracy of the model on the elements, let's say, on all of the elements up to the ith batch is not too far off than the accuracy of the model on the entire data set. And this is less than 0.9. Otherwise, we would terminate, right? We said when we get 90% accuracy on the entire data set, we're happy, we're done. But let's assume that's not the case. On the other hand, I got this amazing miracle local progress condition saying, listen, on the batch, after you do the gradient descent step, you get like perfect accuracy, okay? So just combining these two things together, I know that on one hand, the elements that I'm looking for are the elements that are classified correctly. On the other hand, I know that there are some elements that are not classified correctly. So I can kind of shrink the search space that I have and get a more efficient encoding using the model. Okay, and what's the hint? The hint would be just the relevant tuple and encoding of the tuple in this reduced set of elements. Okay, so let's try to put it all together, at least for this case 2. So again, I start with the data set with the model at the end of the epoch. I have a bunch of hints, one hint per iteration. I take the model and I take the hint. I reconstruct the batch and I do this more efficiently, like in a non-trivial way, because the model reduces the size or the possible number of batches I can pick from. Then using that batch and the model, I can reconstruct the model one step before. Then again, I have the hint, okay, and reconstruct the batch from a smaller set. Again, this is efficient, okay? And I continue to do this until I reconstruct all of the batches, which means I've reconstructed the randomness. And hopefully you believe me that I've saved enough bits using these encodings so that the entropy compression argument holds, which in a similar way would imply that the SGD algorithm that I showed you the code in the beginning has to terminate, which means that you get eventually good accuracy on the entire data set. So let me recap. I will start by recapping the assumptions that we made. So we have this local progress assumption. Then we say that models compute simple functions. So here I'm giving you also the exact parameters. The batch needs to be sufficiently large. Okay, so the dependence on this beta and epsilon parameter, I wouldn't say it's good, but the logarithmic dependence on n, the number of elements, is nice. That's kind of realistic. The goal function should be differentiable and L smooth. And given all of the above, this terminates in O of the Kolmogorov complexity of the data set over beta epsilon to the third n. And just to make this a little bit more realistic, these local progress assumptions and models compute simple functions, they don't have to hold all of the time. They just need to hold for like a gamma fraction of epochs, and then the gamma will appear in the running time. Basically, you'll get a slow running time. Okay, so just like briefly saying something about known results. So there are known results showing convergence for over-parameterized neural networks, and they usually demand that the width of the neural network is pretty big, and then you get the whole thing is pretty big. So you get like a large polynomial. I don't remember what's the state of the art, maybe n to the 6, n to the 4th. And the convergence time is also a pretty large polynomial and to the, at least the 2nd, maybe to the 4th. I don't know of any known results for under-parameterized models. So yeah, if you know, please tell me. Yeah, one nice thing about this is that we make no assumptions about the model architecture, but really, like the most honest way is like to say that our results are not really comparable with known results, because you have this k of x in the runtime. Like, what is that? Like, it's it can be very large, it can be very small, and we have these assumptions which you might say are reasonable, and you might say that are unreasonable. It's completely up to you. Okay, so that's it for me, and I'll be happy to hear your questions.
All right, thank you very much. Thank you. Any questions or comments?
No questions?
No questions.
Yes,
But it was.
Yeah, all right.
No, I just wanted to say that I think the approach is fascinating, and it's really funky way of showing convergence. But really, I think it hinges on this one assumption, right? On the complexity of this accuracy function.
I mean, if you don't like it, how about looking at underparameterized models? So this works also for underparameterized models. And you don't need that assumption. It holds trivially. So what would you say for that?
Maybe I need some convincing that it holds trivially, but yeah.
Well, I mean, do underparameterized models never work?
Do they what?
I mean, underparameterized models, it's a thing, right? I know that the entire community is looking at overparameterized models, but I mean, underparameterized models, yeah.
Is it? Yeah, I'm not sure if it holds trivially. Yeah. So I mean, one is the complexity of the functions. Well, I don't know. It's too hard to.
But the complexity of the function would be always smaller than the complexity of the model. And then if the model is underparameterized, we'll just get it under this bound, right? So that should be fine. But I really
think I have to think about this a bit more. So
yeah, I mean, so I didn't have this in the beginning, but then I while proving things, I understood that I needed it. And yeah, I'll be happy to get rid of it, but I don't see it going away. I just want to say that this approach, you can use it for a lot of other algorithms, and some of these assumptions will sort of go away, okay? So, for example, I try to use this approach for mini batch k-means. It falls very well into this paradigm. And of course, the model is so simple, just k points. You immediately get rid of all of these ugly assumptions. But I proved that using this technique. And then I said, oh, I don't need any of this, and I can just prove whatever I proved using, regular concentration bounds. But I still believe it can fit into some mini batch, something famous algorithm. So if you find something, it would be nice.
Yeah, for me, my interest would be to apply it to kernel flows, as I told you earlier. It's a method to learn kernels for function approximation, where I thought it would be useful.
If it has the structure of sampling batches, then it might work. It really depends on what goes on there.
Yeah. All right, thank you. Any other questions or comments?
I might have a small question. So when you, first of all, thank you very much for this very interesting talk. When you first introduced us entropy compression with this example with the piano keys, you had also that assumption that pressing one key should not affect too much of the light bulbs.
Yes.
Is that, how does this translate in the SGD? I mean, when you use it in the SGD, I might have missed it. I'm sorry if that's the case.
Okay, so if I wouldn't have that assumption, then that problem would just be sat. Okay, like it would just be the general satisfaction problem. So you need some assumption, and what that assumption did, it allowed for things to be compressible. So I didn't really do the math there, so it's kind of, it's hidden. But if you wouldn't have that assumption, then to encode every hint, you would have to use like more bits than you're getting, okay? And then you just won't get any compression going on. The relation here to SGD is that we somehow managed to use the model, of course, with some assumption about local progress and that the model is simple to get compression. So instead of just encoding the batch, we said, no, use the model and encode it in using less bits, or use the model and encode the entire permutation more efficiently. Okay, so yes, so that thing was for that. By the way, I kind of did it with like a very visual thing, but the actual proof of the entire theorem is also not so complicated math-wise. It's called the Moser-Tardosh algorithm. You can find like very nice presentation of it. It's usually like 2 paragraphs.
Okay, thank you very much.
Thank you.
All right, thank you. Any other questions, comments? All right, thank you very much, Gregory, for the nice talk, and then thank you, everyone. So see you in about 2 weeks. Yeah, bye-bye.
Thank you, everybody.
Bye.